Okay, whoops. So we are doing E. So we substitute into our little equation that we have to know. So with the numbers in E, Kimberly, what did you get for your absolute error? Did you get a number?
1.275.
Oh, just give me everything. Okay. You got what? 1.275. 10 to the -6. Okay. That's the whole. Now we know that's not right, but it's just the number in all its glory. Everybody agree with this for the absolute error?
Yes.
Okay. Now let's write it in the way it's supposed to be written. Plus or minus 0. How many zeros? 5. And then we're going to write a 1.
Did you leave it as plus or minus 1 times 10 to the -6?
Oh, yeah. Make sure you just write 1, though, not 1.2 or anything like that. That's a good one. Let's write that. It's a lot easier to write, isn't it? Okay. So does it agree with E? Does this error agree with this? We're supposed to report digits all the way to the 1, 2, 3, 4, 5, the 6th place. All I see is 1, 2, 3. All I see is 4. There's 2 more digits to replace yet. They haven't been reported. You can't assume zeros. They didn't report them. So they do not agree. That does not agree. There's something messed up there. Either the measurement's wrong or the error's wrong. They do not agree, so don't circle it. Okay? Does that make sense?
You're saying that, like say for the 9425,
Yes?
the first figure is the one that you use. Like say there's a 000 and then 9.
Yeah.
You go to wherever the first figure.
Where are the first figures? Let's try to screw you up here. Let's change this 0.09876.5. Now, how would you report? Let's say that's what we got as our absolute error. What would you say your absolute error is? I hear 0.1. I hear 0.10. Okay. This is what I would, in light of what the book is trying to do, well, I should write my plus or minus. That might be a good idea. Plus or minus 0.1. Don't write a 0 after it. That works. But what Kat is saying is I think what the book is really after. Right? Because that's the reason of, that's the only one that I think makes sense of writing that second little digit. But 0.01, this is good. 1 digit makes sense. I like this one, but either one works. Okay? Either one works. Okay. Propagation of uncertainties in mathematical operations. So we just took a quiz where we took numbers divided by numbers plus other numbers. Well, now we're just going to have numbers divided by other numbers plus numbers, but they're all going to have plus or minuses. And how do you handle that? Okay. So in the first case, when the measurements do not have the tolerances, when they don't have the little plus or minuses by them, well, then you just handle it the way we just did. If you're just multiplying and dividing, report your answer to, well, how did it go? The smallest number of sig figs. You have adding and subtracting, and there's no plus or minuses anywhere. All you do is adding and subtracting. Report your answer to the least decimal place. Right, the one with the worst tolerance. Okay, the least resolution, the worst resolution. So that's how we handle this first part. We've kind of already done that yesterday in the quiz today. Now for everything else, for all the measurements that have tolerances with them, we have to use table 3-1. So what's table 3-1? Here it is. Okay. Let's take a little closer look at this. Y equals x1 plus x2. Miranda, what does that probably mean? Y equals x1 minus x2. Y equals x to the a. What is this? How do they want you to read this?
It's like might have like a number and its uncertainty plus a different number with a different uncertainty.
Yeah, that's how they want you to see this. Did you hear what Amanda said? Y equals x1 plus x2. x1 is just some measurement. x2 is just some measurement. Y is your result. Y is your answer. So whenever you have something plus something, how do you know what the error is in your answer? Now, at least they're being somewhat commonsensical when they have E for error, I guess. But that's about as far as it goes. Yeah, now you're seeing it. You're seeing what Kat, you see what Kat's saying? Kat's saying, okay, you add two numbers. x1 has a plus or minus in it. x2 has a plus or minus in it. Right? And how do you get the error in the result? You have to take the square root of that error of x1, square it, add it to whatever the error is in x2, square it. Sum them up, take the square root, and you have your answer.
So your error is still going to be plus or minus because square root, the answer is square root.
Oh, don't worry about this positive plus or minus. It's just the absolute magnitude. So what I mean is, whatever result you get here, it's going to be plus or minus that error. So don't think of we're squaring minuses and stuff. No, we're just talking about numbers. How much? What's the error? What's the tolerance? How big is it? It's always plus or minus whatever that E is. Okay. Now there's one. Before we keep going here, there were two types of error, two types of tolerance. They were called absolute error and relative error. Relative what? No, this percent relative uncertainty. Okay, there's absolute uncertainty and percent relative uncertainty, right? How can you tell the differences? Where'd our table go? How can you tell the differences in here? There you go. Do you see it? If you see let's stick to our top one. If you're taking two numbers and you're going to add them, two measurements, each measurement has a plus or minus to it, you're going to add them, you want to know what the error and the result. You have to use that circled relationship. Okay, now what errors like EX1 and EX2, those uncertainties for those measurements, they don't have a little percent by them. So you have to plug in the absolute for this to work. Okay? If they would have gave you x1 is 1.2 plus or minus 0.8%, and x2 is 3 plus or minus 4%, you have to convert that 0.8% into, what is it called? What type of uncertainty? Absolute. You have to convert the 4% into absolute, and then you can use the equation. And then, moreover, when you get your result, is that an absolute error or is it a relative uncertainty? Is it an absolute uncertainty or relative uncertainty when you get your result? That little EY. It's absolute, and how do you know? There's no what symbol up there? There's no percent symbol up there. So when you get your answer, it's really nice because then you can report your answer to the right number of sig figs right away. You don't have to do any figuring. But look at these guys. If you multiply two of them, if I multiply x1 and x2, I have to use this equation. I'm going to have extra work in the end because I'm going to get my result as a relative, as a percent. Then I have to go and convert it to absolute and make sure it matches my measurement result. Okay, so I think you have a sense of the game, of the rules of the game here. I think I should go ahead and try it. Okay. No, I give you all these tables. But what you need to know, and maybe not, Kat, here it is. You don't even know if you have really good eyes. you can see the equation for relative uncertainty. Right? Otherwise, just know what that equation is for relative uncertainty. That's what you need to know. This guy right here, right? Percent relative uncertainty is absolute over the measurement times 100. Okay, so let's try some of these. Get you comfortable with them. We're going to do this first one. It has pluses and minuses in there. It has tolerances, so that means we have to use the table. And moreover, we have to use the first one. Okay. See if you can get a result for EY. So hopefully you see you're going to have to use this one. Right? And your result is going to be an absolute error, absolute uncertainty. So we can just use it directly, but we need to get it. Did I lose anybody? So yeah, so for EX1, what number is going to be? I guess you call this X1 and that one X2, right? So this would be EX1. So according to the equation, I have to take 0.2 squared plus 0.1 squared. See what you get, square root, and that's your EY. That's your absolute uncertainty. Okay, so did anybody see what I did here? Now this is not right. What should I report it to? 0.2. So, all right. So did I report the measurement correctly? This part has to be plus or minus 0.2. How about the measurement? Yeah. If I needed to add a 0 or something, I would, like 2.10, but I don't. You stop at that tenths place. All right? They have to agree. That's why I think the problems where they give you the absolute in the first place, they're a lot easier, so you don't have to do that extra step. Oh, we will see. Like this one. Oh, I should draw a box around it or something. That's your final answer. Okay. Find the problem you have to use. Find the error equation. You see it? We're multiplying two numbers, right? Here's our measurements. We're supposed to be multiplying them. So we should use the third one down. Good. But we got to convert it. We have to convert these, what type of errors? Absolutes into relative. Relative percent. We have to convert them, otherwise we can't use that equation. And then you get your result, you got to convert it back. According to this, because it gives you it in percent. Try not to do much rounding until the end. I mean, you don't think you have to carry all your digits, but try not to do too much rounding until the end. Okay, back here, set up the equations. You'll have the percent, and you'll have this number that has to equal your x, like Pedro said, divided by the measurement, and solve for that x. Same thing. It would be the measurement. This is your measurement.
Which is going to be the 9.43 times.
Yeah. Yep.
Oh, okay, so you just do that.
Mm-hmm. I carried way too many digits, but that's the idea, right? So I'm not quite done yet, though, because my answer has to match the error, right? My answer 0.15088 plus or minus 6.2724, right? That's not right. You have to get them to match. So the only way is to convert this guy back into, what do they call it? Not relative, but absolute. Get him into absolute. All right, so how would you get him into absolute? All right, well, the percent relative error has to equal the absolute. Pedro likes the x. I like that. All over the measurement times 100. Right? And solve for that absolute. Yeah.
So when you find like the initial percent, you don't have to round it, or you don't have to put it to the fraction digits.
I'm just.
You put 0.53 instead of 0.5, so you don't round up. Well, it's not really rounding, but you don't keep it to that single digit you're supposed to.
I'm carrying all the digits until the very end.
Oh.
And that's where I do the rounding and carry that one digit. I mean, I don't know. That way I'm playing it as safe as I can play it. What did you guys get for x? And there's a bunch, like 4, 6 and stuff, right? Depends on how many digits you're carrying, but I think you're right, 0.009. Plus or minus. Okay, now we can report this guy right. Our final answer, let's do red again. It has to be plus or minus 0.009. Whatever you write has to agree with it. So you would write 0.15, 1, 2, 3. can only go to the third place. Can only go to the third place, right? 1, 2, third place. So you'd write 0.151, right? Because 0.150, you didn't take this guy into account. So what did we do? We just multiplied the question wanted us just to multiply our measurements together. So we did that, right? And then it's multiplying, so you got to look. They're giving us plus and minuses, and all these math operations. When they give you the uncertainty, you have to use the table. And then this is an ugly one because the result comes out in relative uncertainty. But to get the error, take the relative uncertainty of measurement 1, square it. The relative uncertainty of measurement 2, square it. Add them together, take the square root. And we got this. Then we had to convert it back into absolute. Right? And the reason why you convert it back into absolute, otherwise I don't know how else you'd report the measurement. Right? You'd have a much stronger brain than mine if you can write the relative uncertainty here and make it match without doing anything. Someone probably can do that. I can't. Okay. There's another one. We have a couple minutes. See if we can knock this one out. Or you can. Right? It's all kind of the same thing. Let's just finish this. Now this looks to me like it's going to be a multiple step problem, right? Do what's in brackets first. Oh, we already did that? Did they? Oh, so nice if I did that. Oh, so nice. Oh, I'm so glad you noticed that. Okay, so this is 2.1 plus or minus, what did we say? 0.2. Okay. So now you just have to divide it by this guy. Well, that's not so bad, right? One-step problem. Yeah, we're dividing, so what did that table say? Yeah, same error equation. You're squaring the relative uncertainties and summing them up. And then you're going to end up with the relative uncertainty. Find the two relative uncertainties. Jamisa, did you get an answer for this guy? Percent EY? Yeah. Nilo, did you get an answer for percent EY? What did you get? 9.5? Folks are getting 9.5 for that, percent EY. Now you got to go back and convert it into absolute. Oh yeah, we're out of time again. So I got about 0.02 for the absolute. So did you get 0.22 plus or minus 0.02? Great. Great. So have a good day. Come by if you have some questions.